Yeah, thank you very much. And thanks for inviting me to speak in this seminar. So I'll talk about Lawvere theories in general, what they are, and kind of mix in some discussion of the work I've been doing the last month or so, 2 months, formalizing these notions in Lean and trying to make them actually useful, trying to make the formalizations actually useful. So to start off, I think I'll start with an example. I'm going to construct a category, and the objects of this category are just going to be the natural numbers. Okay. I'm going to construct this category by telling you what the morphisms in this category are. In other words, if I take two natural numbers, I need to tell you what's the set of morphisms between those two natural numbers with respect to this category structure. I'll refer to this category that I'm about to construct as L. Okay? So let's get started. For a natural number, I'm going to consider Fn. This is going to just be the free group on n letters. And for whatever reason, I chose x1 to xn for those letters. Okay? Just the usual notion of a free group. And right off the bat, I'm going to tell you what the morphisms are in this category L. So the morphisms from A to B, A and B are natural numbers here. Morphisms from A to B are going to be the group homomorphisms from the free group on B letters to the free group on A letters. So notice the order is reversed here. A comes first here, B comes second, but here B comes first and A comes second. Okay, so this is the definition. But let me play around with this definition a little bit. So the very first thing that I want to do is remind you of a consequence of the universal property of a free group. So the universal property of this free group in particular, f of b, tells you that if I have any group G, group homomorphisms from FB to G are the same thing as functions from the set of generators x1 to xb of this free group to the group G. In other words, we may as well think about this set of morphisms as just functions from my set of generators for f of b to this free group f of a. Okay? So that's maybe the more convenient way of thinking about this collection of morphisms in this category that I'm working with. Okay, let's go a little bit further. So if I take the free group on A plus B generators, that's the same as the free product of the free group on A generators and the free group on B generators. So the star here refers to the free product of groups. Okay, this is a general notion, a general property of free groups. And now we can combine this with our definition of the group structure, of the category structure of L, which will then tell us that if I look at morphisms from C to A plus B in this category L, well, by definition, that's the same as morphisms of groups from the free product of these two groups to this group F of C. Now we can use the universal property of the free product of groups. In other words, a morphism from a free product of two groups to some other group is the same thing as giving a morphism from each component to the free product. In other words, the free product is the co-product in the category of groups. Okay, all that goes to say is that we can identify morphisms from C to A plus B with morphisms from C to A, or rather the product of morphisms from C to A and morphisms from C to B. Okay, which of course is going to be functorial in C, A, and B, which then will tell you that the sum of two natural numbers, a plus b, behaves like the categorical product of a and b in this category. Okay. Okay, so somehow I started just with the notion of a free group on finitely many generators. So that's how we constructed this notion of morphisms between two natural numbers. We just used the definition of a free group and the definition of a morphism between groups. And we obtained a category, L, on the natural numbers where a plus b behaves like the product of a and b in the category. Okay. Well, a similar reasoning then can show you that the natural number 0 behaves like the terminal object in this category. Okay, so this is some abstract construction. Why is it useful? Well, let's dig a little bit deeper. So let's consider the function from, here I'm going to construct a morphism from 2 to 1 in this category. A morphism from 2 to 1 is the same thing as a function from the set with one element to the free group on two generators. The element in the set with one element is what I called x1. And if I look at the function that sends x1 to this product of the two generators in f2, that will correspond to some element to some morphism from 2 to 1 in this category. Okay. Similarly, I can construct a morphism from 0 to 1 in this category by looking at the function that sends x1 to the identity element in the free group on no generators. Oh, sorry. Okay. And that's going to correspond to a morphism, which I'm going to call epsilon, from 0 to 1. And then finally, I'm going to construct a morphism sigma from 1 to 1, which is going to correspond to the map that sends x1 to its inverse in the free group on one generator. Okay. So, well, what we know about the group structure of the free group, namely that the elements in here are words that you can write down in the language of groups, in some sense lets me construct these three morphisms in this weird category L. I have a morphism mu from 2 to 1, a morphism epsilon from 0 to 1, and a morphism sigma from 1 to 1. Okay. Any questions about this so far? It's a bit hard to gauge if yeah.
Yeah. So in each case, are you just picking out? In these cases, you're just picking out an element of the relevant free group, right?
That's exactly right. Morphisms from any natural number to 1 is the same thing as just picking out an element on the free group of the source.
Okay.
Yeah, because these will correspond to maps from the 1-point set to that free group. Okay. Does that make sense?
Yeah.
Okay. Okay, so let's see what we can do with these three morphisms. Let's now take a functor, G, from this category to sets, and I'm going to assume this condition, that this functor sends the natural number n to just the n-fold product of G of 1. All right. Well, we just constructed these three morphisms, mu, epsilon, and sigma. So now we can do something with them. Namely, G of mu is going to be a map from G of 2 to G of 1. And G of 2 is G of 1 cross G of 1. Okay? So G of mu gives me a function from this product of sets to itself. From G of 1 cross G of 1 to G of 1. Similarly, G of epsilon will correspond to an element of G of 1. And G of sigma is going to correspond to a function from G of 1 to G of 1. Okay. Now, exercise. the set G of 1 is a group whose multiplication is G of mu, unit is G of epsilon, and inversion of G of sigma. Okay? And in fact, any group arises in this way. If you start with any group whatsoever, you can construct a functor from L to sets, which sends the natural number 1 to the underlying set of the group. Okay. Even better, if you take a functor from L to C, where C is some other category, which again satisfies this condition, then G of 1 is going to be an object of C. G of mu is going to be a morphism from this times itself to G of 1, and so on and so forth. And this gives you the notion of an internal group object in the category C. For example, if C is the category of smooth manifolds, this will correspond to the notion of a Lie group. If C is the category of schemes, this will be a group scheme. If C is the category of sheaves, of sets on some site, this is going to correspond to a sheaf of groups, and so on and so forth. And conversely, any internal group object in a category with products arises in this way. Okay, so in some sense, what this category L does is it gives us a uniform way of talking about group objects in arbitrary categories with products. Okay, just by looking at product preserving functors out of this category L. Are there any questions about these exercises? Sorry?
That is what, what's G of 1 to the n?
Sorry, I can't quite hear.
Like, what's the power to the n?
This is just the Cartesian product, the n-fold Cartesian product.
Okay.
Yeah. Well, I mean, in a category C, it's the n-fold categorical product
Okay, sure.
of G of 1 with itself. But in the case of sets, this is just the Cartesian product.
Okay.
Okay, so this brings me to the definition of Lawvere theory. A Lawvere theory is simply a category structure on the natural numbers where A plus B is the product of A and B and 0 is the terminal object. Okay, it's a very concise definition. What are these useful for? Well, as we just saw, we can model group theory in some sense, or rather groups, as functors from a particular kind of Lawvere theory to the category of sets. That Lawvere theory is the category L that I just constructed for you. Groups is not special for this definition. I could have repeated the same definition with the notion of a free ring, for example, and obtained a Lawvere theory which corresponds to the notion of a ring. Similarly, I could have started with the notion of a monoid. I could have started with any structure that appears in universal algebra with one sort. Okay. Sorry, let me just catch up on my notes. Okay. Yeah, so as I just said, somehow this definition that I've just described for you and the example that I've just described for you is a bit special because, well, for instance, here, somehow at least on objects, I'm claiming that the value of this functor on any natural number n should be determined by a single thing, G of 1. That somehow corresponds to the fact that when you're talking about a group, for instance, there's just one underlying set involved. But imagine you may want to talk about the notion of a module over a ring. In that case, you would have two sets involved. You have the set underlying the module and the set underlying the ring. You have some axioms that tell you that the ring is a ring, some operations and axioms rather. You have some operations and axioms that tell you that the module is an abelian group, and then you have some additional operations and axiom that tells you that the module is a module of the ring. Okay, that would be an example of a two-sorted algebraic theory. Now, let me just briefly describe how to go from the single-sorted story to the multi-sorted story, and I'll do it in a way that is maybe most convenient for this particular crowd, maybe not as convenient for the average mathematician. The key observation is this, that we can identify the natural numbers with the collection of multi-sets on a single point set, okay? And the sum of natural numbers under this identification corresponds to the disjoint union of multi-sets. Now, if I just repeat the same story, replacing the natural numbers with multi-sets on some arbitrary set of sorts, then I'll get the notion of a multi-sorted Lawvere theory. So here's the definition of a multi-sorted Lawvere theory with respect to a particular set of sorts S. It's a category structure on the collection of multi-sets where the disjoint union is the categorical product and the empty multi-set is terminal. Okay. For example, if you want to model the theory of modules over rings, this set of sorts would have two elements, one for the module, one for the ring. Does that make sense to everybody?
Yeah, I just have like, so free groups, we have free groups which are like indexed by natural numbers, but we could also have free groups like bigger than that, right? We could index by the cardinals or something like this. So
sorry,
that mean,
I didn't quite hear.
which one is, should I go to this one?
The one in the left one.
Okay. So like we have free groups which are bigger than just like, you know, which are generated by more than a finite number of elements. So can you like,
Yes.
Does that actually
Kevin? Yeah. For some reason, my notifications are showing up on this window. Sorry.
so like, yeah, can you like have Lawvere theories which are like kind of in a cardinal index rather than natural indexed, and then
I mean, of course you can. Yes, but maybe the observation to make here is that the free group construction commutes with colimits because it's a left adjoint. So, and you can write any set as a colimit of finite sets. So therefore, in some sense, a free group on a general set is determined by free groups on the finite subsets of that set if we take some colimit.
Sure. Okay. Yeah.
Okay.
So you don't need to go to fin sub instead of multi-set.
Yeah. Yeah. But yeah, there is the notion of an infinitary Lawvere theory, which is not quite related to doing the analogous thing where you take the free group on an infinite set, but rather it's more analogous to being able to take infinitely many, a product of infinitely many sets in some sense. Okay, well, I'm not going to talk about that in this case. I'm just going to focus on this notion of a Lawvere theory. Okay. Okay. Great. So this is in some sense, the standard definition of a multi-sorted Lawvere theory with a set of sorts S. If you look at the NLab, for example, you'll see a slightly different variant of this definition, but I think this is something that for people that are familiar with formalization is maybe the most familiar. Let me just discuss a little bit. If we look at somehow the Lawvere theory corresponding to the trivial algebraic theory, in other words, just equality, okay? The Lawvere theory associated to that is in some sense the free category with products generated by the set S. What does that mean? Well, somehow you look at the smallest category structure on the multi-sets of S, where the disjoint union is the product and the empty set is the terminal object. In this case, you can imagine that this category satisfies a universal property. If this is really supposed to be the free category with products generated by the set S, what that universal property would say is that functors from this category to C, which preserve finite products, should correspond to just plain old functions from the set of sorts to C. Now, indeed it does, but there's a small issue, especially if you're going to go formalize this definition. There's going to be a small issue that you're doing something quite evil in the sense of category theory. There's an identification of objects happening here. For example, if you think about this multiset xy, and you have such a functor f, which should correspond to a function little f, where should this functor send this multiset? Should it send it to f of x cross f of y, or f of y cross the terminal object cross f of x? Now, yes, it is the case that this object in the category C with products in the terminal object is isomorphic to this object, but they're not equal. So you have to make a choice. You have to choose whether to send this element to this guy or to something like this, or to something more complicated that's somehow isomorphic to an object of this form. Okay, so again, as I said, when you're going to go formalize this definition, this sort of issue will cause problems. So instead of working with the collection of multisets in generated by a set of sorts S, it turns out to be much more convenient to do something a little bit different. Namely, and now I'm going to start moving a little bit more towards the formalization part of this lecture. Instead of working with multisets, I'm going to work with this inductive type. Okay? So what I'm doing here is I'm starting with a set S, or rather a type S, and I'm constructing this inductive type, which has three constructors. One for elements of S, one which is supposed to mimic the product, and one which is supposed to mimic the terminal object. Sorry, this highlighting is not quite working. So this nil is supposed to mimic the terminal object. Now, of course, the type of multisets of S is a quotient of this inductive type. At least the finite multisets are. Yeah. It's a quotient of this inductive type, but it's a non-trivial quotient. So there's really some identification happening. But because essentially of this discussion that this should be the free category generated by S with respect to products and existence of terminal objects, it turns out that it's more convenient to use this type as the type of objects for that category as opposed to the type of multisets. So finally, let me write down for you the definition of the Lawvere theory using this approach. Okay, it's once you make the change from multisets to this prod word inductive type, you just follow your nose and write down the naive definition. In other words, a Lawvere theory on S is a structure which contains some type of morphisms between any two such elements of this inductive type. You should have an identity morphism. You should have a notion of composition. You should have a projection onto the first component, which would somehow view the product of H and T as the categorical product. Similarly, you have a second projection. You have a lift morphism, which goes into the property that this product does indeed match the categorical product. This is essentially what we use to encode the universal property of the categorical product. And then you have a morphism to what's supposed to be the terminal object, namely this nil element in the inductive type. And of course, you have some axioms, which I've omitted from the slide because there are several of them. You have the axioms that say that these three pieces of data form a category, namely the composition is associative, that composing with the identity doesn't do anything. You have the axioms that say that this product in the inductive type prod word should behave like the categorical product. Again, I've omitted those axioms. And then you have a single axiom that says that this is indeed the terminal object. Okay, So quite straightforward. Now, once we have this definition, we can quite easily also talk about internal objects associated to the Lawvere theory. The terminology in the literature is not to call such objects internal objects, but rather to call them algebras for a Lawvere theory. So that's what I've called them here. Let me just, there's some terminology here that I'm not going to spend too much time on, but essentially what's happening is that I have a Lawvere theory, L, kind of like the category script L that I've described for you earlier as the main example that I started with. You have some other category C, and an algebra consists of simply a functor from the category associated to L to C, which preserves binary products, okay, and preserves terminal objects, right? This is just how you spell the fact that this functor preserves products and the way that products are formulated in Lean's math library, MathLib, and this is how you spell the fact that it preserves terminal objects, okay? Okay, so, you know, this looks like, this is a structure with, let's see, 1, 2, 3, 4, 5, 6, 7 pieces of data. These axioms, I think there's 3 axioms here. This also has 3 axioms, and this has 1 axiom. So that's 7 axioms and 7 pieces of data. So that's 14 fields altogether that one would have to construct to even talk about a Lawvere theory. Okay. Even worse, you somehow have to construct this type of kind of general morphisms in this category, which somehow should correspond to the theory of groups, for example, or the theory of rings, something that should be quite straightforward to write down. So the main thing I want to talk about for the rest of the lecture is the issue of how to actually construct these objects. Are there any questions before I proceed to this?
In your actual formalization, do you make Lawvere theories a new structure, or could you not just sort of extend the existing definition of a category?
Yeah, that's a good question. So you can, like for example, this hom, id, and comp are the fields of what MathLib calls like a category struct. And then the axioms extends that category struct with the axioms of a category. So somehow I could have formulated this first chunk, for example, as a category instance. And similarly, I could have phrased this chunk as the existence of some limit cone in the category structure, and this is the existence of some terminal object. The issue with this is that if you fix a type of sorts S, the objects will essentially always be prod word S. And the way that category theory works in Lean with the current setup is that it's a type class on top of the type of objects. So in principle, if I have 2 Lawvere theories with the same type of sorts, I would have to talk about 2 category instances on the same type, and that's bad.
Wait, do you mean that
okay.
if you show extending the type class, then you get the instance from the structure to that type class?
Again, I can't quite hear you.
We should go.
Yeah.
Yeah, so I think Yale's question was, if you have a structure that extends a type class, then are the instances of the structure recorded as instances, or like just plain old objects? Is that your question?
Oh, I see. Okay, I see what you mean. Yes. Okay, you're right. So I could have somehow not registered the category instance on prod word S. That would have been fine. But then somehow using the category structure doesn't buy you anything useful, because you somehow still have to construct another category structure on an alias of prod word S associated to a Lawvere theory L, right? And that's essentially what's happening with L.cat. Okay. So at the end of the day, the 2 approaches will be equivalent, but I found this approach to be slightly more convenient to avoid somehow confusion with notations.
Yeah.
But okay, anyway, thanks for the question. Okay, so yeah, I'm going to talk a little bit about how to construct Lawvere theories. So here's the general idea. If we take an algebraic theory, like the theory of monoids, groups, rings, and so on, we can associate, we can consider the category associated to that algebraic structure. Like, for example, if I have the notion of a monoid, I can look at the category of monoids. If I have the notion of a group, I can look at the category of groups. If I have the notion of a ring, I have the category of rings, and so on. And we also have the corresponding forgetful functor, which ascends, for example, a monoid to the underlying set of the monoid, or a group to the underlying set of the group. By general nonsense, we know that such functors always have left adjoints. These left adjoints, in the case of groups, for example, are is just a functor that sends a set to the free group on that set. Okay. And once we have somehow this functor and its left adjoint, which is unique up to isomorphism coming from this functor, we can mimic the construction that I went through in the first example to construct the Lawvere theory associated to that algebraic theory. Okay. And I put a little exercise here in case anyone wants to figure out how to do this in the multi-sorted case. It's possible to do, but it's not so straightforward. Okay. And there's somehow a theorem that underlies this. I don't actually know who to attribute this theorem to. I assume it's to Lawvere himself. But in any case, the theorem says that whenever you have a concrete category which satisfies some properties, which I can talk about more, but maybe it's not necessary. These properties are that the forgetful functor is monadic and it preserves certain kinds of colimits. Then it turns out that C is indeed equivalent to the category of algebras of some Lawvere theory, at least a single sorted one. And the converse of this holds true as well. And once you have the category of algebras, for example, in the case of L that I constructed in the first example, the category of algebras of L is simply the category of groups. Once you have that, again, using the same process in the example, I can construct the Lawvere theory itself. And again, there's an analog in the multi-sorted case. So this is quite a nice and convenient theoretical characterization of Lawvere theories, but it doesn't quite help us construct anything explicit. For example, if I start with the usual notion of a group as a set with a binary operation called multiplication, a unary operation called inversion, and a constant called the unit, which satisfies the axioms of a group, it's not so obvious how to construct the Lawvere theory out of it without first constructing the category of groups and going through this kind of abstract nonsense left adjoint approach. Okay. The solution to this is what I'm going to call a Lawvere presentation. This is essentially what historically has been called theory in the context of universal algebra, but just formulated in a slightly different way in the context of Lawvere theories. So here's the definition. If I have a set of sorts, I'm going to say that a Lawvere presentation for that set of sorts consists of this data. Whenever you have an object in this inductive type that I mentioned for you earlier, and an object of S, you need to specify a set of operations from A to B. So for example, if I want to mimic the operation of multiplication on a single sorted Lawvere theory corresponding to groups, then S would be a single point set. The A, in that case, would just be the product of the point with itself, which is a term of prod word. B is going to be the point itself. And I would have a single element corresponding to multiplication, which would correspond to a binary map, a binary operation on the set underlying the group. So these are somehow the operations that are going to appear in my algebraic theory. And then I need to somehow formulate the relations. And to do that, I have to write down, again, some notion of what it means to somehow compose these operations. And you can formulate this in terms of, well, expressions in some sense, which you can write down in an arbitrary Lawvere theory. I ended up calling these things Lawvere words for one reason or another. In any case, you should think about number 2 as somehow codifying the equational axioms in an algebraic theory, like the axiom of associativity in a monoid, for example, is such an example. So here's the actual definition of this inductive type of Lawvere words. We have some notion of operations, which takes prod word S and a term of S and gives you a type of operations from this object to the object there.
I think
and you construct an inductive type that takes,
we have a question in the audience.
Yes. When you defined your things on the last slide, you with the prod words, because you haven't modded out by like associativity and identity, does that operations have to have some sort of compatibility?
Nope.
Right? Is there no compatibility requirement? Okay.
No. I mean, you can have 2 Lawvere presentations that give you equivalent Lawvere theories.
But what if I have, like, you know, a ternary operation, and then it matters whether my word is like it matters the order in which I paired up my inputs, because prod word doesn't mod out by associativity, right?
That's right. It does not. But I mean, you can imagine a situation where you have an algebraic theory which somehow, I mean, this is like, think of this as like the presentation of a group in some sense. These are the generators, and then these are the relations. So you could add some compatibility in a relation between 2 presentations of what should be the same operation. But a priori, that doesn't need to happen.
All right. Okay. Thank you.
Okay. It doesn't need to happen a priori. Okay. In any case, this is, I just wanted to quickly mention this type of Lawvere words because this is what you need to write down to formulate these relations. I see I'm running short on time, so let me not say too much about this. Essentially, it's a technical inductive type that you need to use to write down the notion of a relation in the Lawvere presentation. And then finally, this is what a Lawvere presentation is. It consists of some type of operations between a term of prod word S and S. And then for any prod word X and Y and S, you have some relation on these words that you generate out of this Hom field. Okay. Now, as I just mentioned, just like you can construct the group associated to a presentation, you can construct a Lawvere theory associated to a Lawvere presentation. Essentially, what you do is you take the category whose objects are given by prod word S, and morphisms are somehow generated by these modulo these relations, and additional relations you need to write down so that the resulting category is indeed a Lawvere theory. Let me quickly explain what those relations are. Again, it's some inductive relation, some gigantic inductive relation, which if I have a relation in the presentation, I get a relation in that inductive relation. It needs to be an equivalence relation. It needs to satisfy the axioms of a category. In other words, if I compose with the identity on either side, it should remain the same, and it should be associative. I'm going through this quickly because I want to get to some actual demo to explain how to work with this in practice. There needs to be a congruence property for composition of morphisms. You have axioms that ensure the universal property of binary products. and that this lift operation is compatible with the relation. You have, again, an axiom that tells you that the terminal object is a terminal object, and that's it. Okay. So a few things we can do quite directly with such a presentation are, well, as we just saw, we can generate a Lawvere theory satisfying a certain universal property. But even better, we can actually construct internal objects associated to a presentation quite directly. And this universal property from item 1 lets you quite easily go back and forth between the notion of an algebra associated to a Lawvere theory that I discussed right earlier in the talk, and kind of this direct notion of an internal object associated to the presentation. Where am I? Okay, so for instance, this universal property, here's one aspect of this universal property. If you have the object field or a function from the type of sorts to some category C, you have a way of mapping the morphisms in the presentation, which is compatible with the relations, then you actually get a monoidal functor from the associated Lawvere theory to the category C. Okay, this is part of the universal property. And let me show you briefly what the internal object structure looks like. Essentially, it has the same fields that you plug in to this lift operation, which is part of the universal property. Okay. Okay, as I said, I'm running short on time, so I want to do a simple example with actual code just to illustrate how to do this in practice. And the main thing I want to illustrate is that even after doing the simplification where we go from a general Lawvere theory to a presentation, it still can be quite tedious to actually construct such things in practice. Okay, so let me do this example here. So this is a very basic class I called foo.
Could you?
Is this okay?
Yeah, that's yes.
Okay, so it's a single sorted class. Okay, I just have one type parameter m. It has a multiplication and a 1, and a single axiom that says that when I multiply x by 1, I get x. Okay, quite straightforward. Now, I need let me briefly explain how to write down a presentation associated to this. Well, first we need a type of sorts. I could use somehow the standard single element type in Lean, but for reasons which I'll get to in a moment, I'm going to define a new type called foo sorts. Okay, which has a single constructor called m, corresponding to the single sort m here. Okay, that's the type of sorts. Now I need to construct the type of operations, which again is going to be an inductive type. And its type is going to be prod word so prod word foo sort to type, and it's going to have two constructors, one corresponding to multiplication, one corresponding to 1. And multiplication is going to be an operation from prod word prod of m m. In other words, I take the product of m with itself, and then I have an operation from that product to m. That should correspond to this binary operation mul. Similarly, 1 is going to be an operation from the terminal object to m, because it's a constant. Okay? And then finally, I need to construct the inductive foo rel, let's say, which takes a prod word on foo sort, foo sort, a Lawvere word on foo op from A to of B, and another one, and gives me a proposition. Okay, so I'm constructing an inductive binary relation on this type of Lawvere words. And let me go down to my cheat sheet because this one is a bit tedious to write down. Where is it? This one. Okay, so just for the sake of time, this is how you would somehow formulate the mol1 axiom with respect to these Lawvere words. And you see it's not very convenient, right? it's a bit tedious to write such things down. Okay, but then we can quite easily construct a Lawvere presentation on foo sort, where ham is foo up and rel is foo down. Okay, so this is the Lawvere presentation associated to this class in some sense. Once I have such a Lawvere presentation, so let me call it something, I can construct a Lawvere theory on foo sort just in the canonical way that takes any Lawvere presentation and constructs a Lawvere theory in this free way. Okay, I have just a couple more minutes. Let me just mention that this is still not ideal, okay? Even in the simple example, it's quite tedious to, for example, write down this axiom. Imagine I have like, I don't know, the axiom for associativity of a scalar multiplication of a monoid acting on a set or something like this. The actual relation would be extremely difficult to write down by hand. And as I said in the slide, we can solve this with metaprogramming. So this is the last aspect of this project that I only have just 1 or 2 minutes to talk about.
Oh,
and that is, sorry?
Oh, we can go on for a couple more minutes.
Okay. So yeah, I'll just talk for just 1 or 2 more minutes. So the metaprogramming aspect of this project essentially is that you don't need to do any of this. All you need to do is use a certain attribute that I call the verify, which constructs all of these objects for you. So for example, it constructs a foo.sort type, which is an inductive type with a single constructor. It constructs op type, which is an inductive type with 2 constructors, one corresponding to multiplication, one corresponding to 1, with the correct types. It constructs rel crop, which is the binary relation. And you can see that it does it in a slightly different way, but turns out to be equivalent. And it constructs a notion of an internal object associated to any category C, which has chosen finite products. To finish this discussion off, let me just briefly illustrate how to use this internal object in practice. This metaprogramming part of the project is still not quite done. There's still some parts that I need to automate. The main thing I wanted to automate, and I wanted to show you roughly how things are defined under the hood, is how to go, say, from an internal object in type to an instance of this class and back. So let's do an example. If I have an internal object in type, then, well, I should get an instance of foo of this type, which is the underlying sort of that internal object. So let's see how to do this in practice. Again, as I said, all of this will eventually be automated as part of this attribute, but it's not quite done. The main thing I wanted to illustrate is that this automation has been set up in such a way so that things behave very nicely in a definitional sense. For example, the multiplication is going to be the function that sends x and y to x map mul xy unit. 1 is going to be x map 1 unit. Mul 1 is fun or conger fun. Let's say this is going to be x rel. What's it called? Mul 1 x unit. Okay. So as you can see, quite directly, this almost looks identical to the actual definition because the names have been chosen in such a way and the objects behave very nicely definitionally. Conversely, if I have a type M which has an instance of foo, then I can construct an internal object by sending M to M, mul somewhere, 1 somewhere. Let me see. Mul should be fun xy to foo mul M is M xy. 1 is going to be foo 1 and M, and then rel is going to send mul 1 to foo, what's it called? Mul 1 M is M. X. And I think I need to say a little bit differently. Just a second. I think I need the fun X. Okay, let me go to my cheat sheet because again, I almost had it right. I just forgot an arrow for the fun X. Okay. So there we go. Almost directly from the definition, we can go back and forth between an internal object of this Lawvere theory, or this Lawvere presentation rather, and an instance of this type class. Okay, I think I'm pretty much out of time, so let me stop here. Yeah, thank you very much.
Thank you. So are there questions over here? Yeah, there's one question by you.
Is this going to be in Mathlib?
I'm working slowly but surely on opening pull requests for this. So right now I've started, there's an open pull request just for this notion of category with chosen finite products, which is something that you need to make these sorts of constructions work nicely definitionally. Next thing I'll work on is PRing just the definition of a Lawvere theory and Lawvere presentation and such things. This meta stuff, as I said, is still a work in progress, but eventually once it's finished, I'll try to get it into Mathlib. Yeah.
There's one question online.
Yeah, thank you very much. This was really, really cool. My question was, have you played around with internal foo objects in categories other than types? Like people say, you know, a ring object in category of sheaves is a sheaf of rings, blah, blah, blah. Have you experimented with those?
I mean, not directly, but again, for example, if I want to look at, say, internal objects in the category of pre-sheaves, to the way I know exactly how to make that work nicely, in the sense that what you have to do is just write down an instance for this class of chosen finite products in the category of pre-sheaves of sets, or taking values in sets, let's say, in types. And just the general formalism of Lawvere theories tell you that you can whisker internal objects, in the sense that if you have an internal object in C and an internal object in D, and a functor from C to D which preserves finite products, then you can compose and get an internal object. You can take an internal object in C, compose, and then get an internal object in D with good definitional properties. So in that sense, somehow, for example, if you're interested in sheaves, because the product of sheaves, the underlying pre-sheaf of a product of sheaves is the product of the corresponding pre-sheaves. If you formulate things correctly in the sense of this chosen finite products class that I'm working on getting into MathLib now, things will work out nicely definitionally. So yeah. But again, not directly, but in theory, yes.